Hello and welcome to our lesson on derivatives of inverse trig functions. Now, I'm hoping we remember what inverse trig functions are. Inverse trig means if you give me a sine and plug it into inverse sine, output will be the angle or radian measure that will give you that fraction. So let's start by looking at just generalities for inverses. On this same grid, we want to graph the inverse of the function that we have graphed below. So let's look at number 2 below that. It says the property of inverses graphically, and the graphs of f and f inverse, again, this is f inverse right here, they are mirror images across the line blank. Well, that line is the line y equals x. So more than likely you've done this before where you had an actual grid. We don't have an actual grid, but if you have a ruler that would be helpful. And we're going to draw in the line y equals x. So we'll say that this is the line y equals x, and it should go directly through the middle, basically bisecting that 90-degree angle there. And when we want to draw the inverse of what I have graphed here, I need to reflect the image that is in black over the red line. So first I'm going to start with the points that are on the red line because those points are going to stay exactly where they are. The next thing I'm going to look at is where the black graph crosses the y-axis. It's going to cross the same location now on the x-axis. And then I'm going to make a mirror image of this figure. So approximately like that, so that if I were to fold along the red line, those two should match up. Mine's a little too fat, the blue one. I apologize, but that's the basic idea, is that they are inverses of each other. They're reflections across the line y equals x. Moving on to number 3. If I take the function and I plug in the inverse of the function at x, what do I get? Well, basically a function and an inverse, they will undo each other. So if I take x, I plug it into the inverse, and I take that thing and I plug it into f, that's going to give me what I started with, x. Same idea with the next one. If I take x and I plug it into f, and I take that thing and I plug it into the inverse, I'm also going to get x. The next question is, what's the difference between arctangent of x and y equals tangent inverse of x? And it depends on what textbook you're looking at. Some textbooks will differentiate between the relation and the actual function. For the function value of the inverse tangent or arctangent, you have to limit your domain so that you have a function, because basically you get something that continuously repeats itself. Sorry, that's not a good one. Something along these lines, it's going to repeat and repeat and repeat. And by the vertical line test, I no longer have a function. So the reality that we live with here is we're going to use these interchangeably, although again, depending on the textbook that you look at, one of them may identify arctangent as the function and tangent inverse as the relation, or vice versa. So for our purposes, we're going to treat them the same. So let's look at the derivative of the inverse tangent function. So we're going to walk together through this, and this is how we're going to actually develop what the formula is. In the end, you'll probably want to memorize the formula, but I'm also going to ask that you be able to derive the formula for the derivative as well. So let's start with number 5. We need to manipulate this equation so that there's no longer an inverse in the equation. I know nothing about the inverse trig derivatives. I know little about inverse trig at all. So let's get rid of it. I don't want to have it anymore. So what would I have to take the tangent inverse of x? What would I have to do to that so I no longer had a tangent inverse? And the answer is, well, if you take the tangent of the tangent inverse of x, I would no longer have a tangent. So if I do that on one side of the equation, I most certainly need to do it on the other side. So I need to also take the tangent of y. So basically what I've done right here is I have taken the tangent of both sides of the equations. Because if y is equal to the tangent inverse of x, and I take the tangent of y, and I take the tangent of tangent inverse of x, those two things should still be equal. I would still have an equation. And when I simplify this even further, I still have tangent of y on the left, and that will be equal to the tangent of the tangent inverse of x, and using the property we had in number 3 above, we know that that's just x. So, number 6, I need to represent this equation with the diagram, and we're going to make the diagram look like something from geometry class, i.e. a right triangle, and we are going to label everything in terms of x. So I'm going to start myself with a right triangle, and I'm going to rewrite what I have, and that's the tangent of y is x. Well, but when I did right triangle trig in geometry, and when you did right triangle trig in geometry, tangent and sine and cosine were always fractions. Fractions. Right now I don't have a fraction. I have tangent of y is equal to x. I need to make that to a fraction. So x is the same as x over 1. So now I have a fraction. So first and foremost, what's my angle called based on this equation? Well, I'm taking the tangent of y, and whenever I take the trig of something, that something should be an angle. So I'm going to label this as angle y. And then I know the tangent of y is x over 1. And let's refresh our memory for tangent in a right triangle. That is opposite over adjacent for tangent. So the side opposite the x, the opposite the y should be x, and the side adjacent to the y should be the 1. And then what I need to do is I need to find the hypotenuse. And I can't find what it is as far as a number goes, but I can find what it is in terms of x. So let's use Pythagorean theorem. C squared will equal x squared plus 1 squared. I don't want c squared, I want c, which means I really need to take the square root of both sides. And again, take the square root of both sides, not of each term, but both sides. So when I take the square root of c squared, I get c. And when I take the square root of the right side, I get the square root of x squared plus 1. Now that can't be simplified. That can't be the square root of x squared plus the square root of 1. It stays just as it is. So I'm going to replace my c in my triangle, and I'm going to put in the square root of x squared plus 1. That's my hypotenuse. So I've done my geometry for the day. We're going to move on and do some more calculus. However, we are going to come back and reference this triangle. So turn the page to number 7. And it says, using your equation from number 5, find the derivative of both sides with respect to x. And be sure we're using the chain rule, the inside-outside rule. Well, I don't really know what that means. To find the derivative of both sides with respect to x. So if you look at A, there is an example. So if I start with sine of z equals q, find the derivative of both sides in terms of q. So to do that, I take the derivative of sine of z, and that's cosine of z. And then I take the derivative of the inside, which is z. I don't know the derivative of z in terms of q, so I literally write it as dz dq, the derivative of z with respect to q. And then I have a 1 over here. Well, really what I wanted to do is I wanted to take the derivative of q. That would be the derivative of q with respect to q, and dq over dq is simply 1. We're going to do that process with our equation from number 5. I'm going to turn my paper over. Let me find number 5. Oh, this one I have in black over here. Tangent of y is equal to x. Once we have manipulated our equations, there was no inverse trig. So that's the equation I want to use. Tangent of y is equal to x. So let's take the derivative of this. So I'm going to start here. The derivative of tangent y is secant squared y, that's the outside, times the derivative of the inside, and we're taking this with respect to x, so that would be dy dx. Oh, look, the derivative of y. That's pretty helpful. And then I want the derivative of x with respect to x, which is dx over dx. Now that is actually, this dx over dx is really just a 1. So what I have now is secant squared y times dy dx is equal to 1. And then in part B, it says solve for dy dx. So I'm going to get dy dx by itself by dividing both sides by secant squared y. So dy dx is going to be 1 over secant squared y. And 1 over secant, sorry, I'm running out of room here. 1 over secant y is being squared, but I know what 1 over secant y is, and 1 over secant y is just cosine of y squared. So I found my derivative after all of that. I found the derivative of y. But let's go back. Go back to the original problem. So turn your paper over. Let's go back. And what were we finding? The derivative of y equals tangent of x. And look at that. We found the derivative of y. We found dy dx. Go back to where we were. Now what it says is, great. We're on number 8. Using your diagram from number 6, rewrite your equation from 7b so that dy dx is in terms of x. That's my only issue that I have right now, is I've got this y right here. Now I can't go ahead and put in tangent inverse of y of x, because that is so not helpful in anyone's world to have cosine of the tangent inverse of x quantity squared. That doesn't make any sense, and it doesn't help anyone. So what I want to do is redraw the triangle that I had from number 6. So that triangle from number 6, I had y here, and I had a tangent of y was x over 1, and I believe we found the hypotenuse to be x squared plus 1. So now I'm going to use my geometry again to rewrite cosine y. I don't want to have cosine y, but when I come over to this triangle, could I find cosine y? I certainly could. Cosine y is, let's see, I think it's adjacent over hypotenuse. So I'm going to come to my triangle. Here's my angle. Adjacent is going to be 1. So cosine y is going to be 1 over hypotenuse is the square root of x squared plus 1. So now all I need to do is I need to substitute. So I'm going to be substituting into the equation I had here. So now I have dy dx is going to be 1 over square root of x squared plus 1 quantity squared. And all I did was I replaced the cosine y that I had over here with the information I had from the right triangle that I started with. And when I simplify that out, I get 1 over x squared plus 1. Now, that is something you probably want to memorize. And I wrote over my my number 9, so I'm going to rewrite it. If I start with y is the tangent inverse of x, then I know the derivative, y prime, is going to be 1 over x squared plus 1. If you memorize that, your life will be much easier. So let's look at number 10. Number 10 says, okay, using this formula, basically, that we just found, let's find the derivative of y equals tangent inverse of 3x. We need to recognize we no longer have an x anymore, we have a 3x. So wherever I saw an x, I need to replace it with 3x, and then I need to remember to use the chain rule, the inside-outside rule. So the chain rule is the rule that I have to use here. So let's rewrite what I have. I have y is equal to the tangent inverse of 3x. And I need to remember that I have a 3x, not an x. So my derivative is going to be 1 over, no longer am I going to have x squared, I'm going to have 3x. It's going to be squared. and then I need to multiply by the derivative of the inside, and my inside is this 3x, and the derivative of that is 3. And if we simplify that just a little, we have the 3 on top, and we have 9x squared plus 1 on the bottom. So that will be my derivative right here. The next one that I want to look at is the inverse secant function. Um, this one I wanted you to do on your own, so I would like you to actually give it a go. Don't worry about the two diagrams in the coordinate plane. I'll talk about that in just a minute, but I'd like you to go ahead and try and do this one exactly the same way we did the tangent inverse one. So rewrite it, take the secant of both sides, draw your right triangle, fill in all the sides, do a derivative, work that out, and do substitution from your right triangle. So go ahead right now and pause the video to work on the secant inverse of x derivative. Okay, so I worked this out, and my derivative is down at the bottom. I'll go ahead and put a circle on that. And I got dy dx is 1 over the absolute value of x times the square root of x squared minus 1. And I can speak to why the absolute value is there. I'm going to go ahead and walk through this. So if you did not get that, go ahead and listen while I walk through what I did. On the beginning step, I just went ahead and took the secant of both sides because I did not want to have a secant inverse anymore. And when I simplified that, I got secant of y is equal to x. And you see I've circled that in red, and this is what we're going to use to actually find our dy dx, and I'm going to do that over here at the right. And I'm going to pause on doing that for just a minute. So continuing down, I need to make my right triangle. So the next thing I did is I rewrote secant y as 1 over cosine y, and I rewrote my x as x over 1. I simply cross multiplied here because I really want to get cosine y by itself. So I ended up with x cosine y is equal to 1, and then I want to get cosine y by itself, and I get cosine y is 1 over x. That is an easy, simple right triangle for me to work with. So I drew my right triangle. Y is the angle, so y goes into my angle position, and I have adjacent over hypotenuse, so 1 is the adjacent. It goes next to the y, and x is the hypotenuse. The next thing I need to do is I need to find, well, I need to know this side that I've labeled b. To do that, I did a Pythagorean theorem, and I have x squared is equal to b squared plus 1 squared. I need to get b by itself, so I subtracted 1 from both sides, and I got x squared minus 1 is equal to b squared. Then to get b all the way by itself, I need to take the square root, and I end up with this last thing down here, that b is the square root of x squared minus 1. Went back up to where I was finding my derivative. First thing I did is I rewrote that I had secant y is equal to x, and then I took the derivative. The derivative of secant y is secant y tangent y, and then it's a chain rule times the derivative of y with respect to x, because y was the inside of my secant, right here. And then the derivative of x with respect to x is just dx dx. In my next step, I simply rewrote my dx dx as a 1. In the next step, I changed my secant of y into a 1 over cosine y, and I did that in blue. And then I went immediately to my right triangle. So in blue, I changed my 1 over cosine y to be 1 over cosine y, and I knew cosine y was 1 over x. I can get that from the triangle, or I can get that from what I have circled in green. Then I took the tangent of y using my right triangle, and that's opposite over adjacent. So I started with y, and opposite y is the square root of x squared minus 1. Adjacent to y is 1. And then I still have my dy dx, and that was equal to 1. At this point, I'm trying to get dy dx by itself, and I have a 1 over x, which is really just an x. So I divided x to the other side. So the 1 that was red is now divided by the blue x. And now I still have to divide both sides by the square root of x squared minus 1, which is what I did to get to my last step here. Now this absolute value of x is a tricky little bean. In essence, we're dealing with the secant inverse of x, which has a restricted domain. The domain for secant inverse of x is from 0 to pi. The problem with that is when I get into the second quadrant, my hypotenuse ends up being a negative polar, basically. It's kind of like we're graphing in polar. And when I go to the second quadrant, my hypotenuse, which is my x right here, ends up being negative in the second quadrant. Here I have a -1, and technically I have a positive square root of x squared minus 1. And so this entity here ends up being negative. Now, because that entity is negative, based on polar, I actually have to take my x down in the opposite direction. When you take your x down in the opposite direction, what you end up with is this triangle, where this is a negative x down here, this is a 1, and this is a negative square root of x squared minus 1. Okay, well, the whole point is once you go to multiply, you're going to end up multiplying these two guys together down here, which gives you a positive x square root of x squared minus 1, no matter whether that your x value over in this quadrant is actually a negative x value, because my x's are negative over here. And when I multiply those two beings together in the first quadrant, which would be these two here, I end up being positive. So regardless, no matter what, my x value has to be positive, which is why the mathematicians said, hey, let's just make that an absolute value, then we don't have to think about it anymore. So this is the formula you want to memorize. dy dx is equal to 1 over the absolute value of x times the square root of x squared minus 1. I'm never going to ask you why that x has to be an absolute value, and if you don't understand it, that's fine. We are going to address polar coordinates later in the year, and hopefully we can get that question answered then. So hope you enjoyed your video lesson. Please bring any questions to class.